Okay. Do you see full screen?
Yes.
Okay,
Great.
great.
All right. So thanks a lot for the opportunity to speak today. My name is Spencer Gessner from SLAC National Accelerator Laboratory. I'll be presenting on behalf of the 10TeV Wakefield Collider collaboration and giving a status update about our design study. Okay. So what is the 10TeV Wakefield Collider design study? Um, we aim to produce a unified, self-consistent concept for a 10 TeV parton center of mass collider based on Wakefield accelerators. So Wakefield accelerators are this very high gradient acceleration technology, and the idea is that it's a linear collider where the actual linacs are short because the gradient is so high. The study was initiated by the 2023 USP5 report. You can read more about it in section 6.4 of the report. So it is sort of a kicked off in the US, but it is a global undertaking. And we're partnering with efforts abroad, specifically Allegro, HAF, and Alive, which are all European efforts, XCC here at SLAC, and the LC Vision program, which Tor discussed in his talk on Higgs factories. Um, and unlike past efforts where members from the advanced accelerator community attempted to do straw person designs of future colliders, in this effort, we are engaging much more strongly with the high energy physics community. So we're talking to theorists and detector physicists about how this uh, machine would be built and what it would deliver. And then, of course, we're also talking to people who have expertise in linear colliders in general. So these are people who've thought a lot about beam delivery systems and how they scale with energy. So those types of considerations. We are a very active community. We meet regularly, and there are links to sort of our ongoing Indico meeting series. We met in person back in March uh, as part of the Allegro workshop. So Allegro is a ICFA initiated, primarily European, but it's technically a global effort to work on these designs for future linear colliders at the energy frontier. We had 100 attendees, many students, many postdocs. Um, we had great discussions. We had people who were critical of Wakefield Collider concepts come and give talks and sort of point out weaknesses in the design. We really want to, understand where the work needs to go. And so, in this particular case, Tor Robbenheimer was the person we called up to poke holes at our design and tell us what we need to do better. And I think it really helps to guide our R&D program moving forward. There will be another Allegro workshop at INFN Frascati in March of next year. Shortly after this meeting, we submitted our input to the European strategy with over 200 endorsers, which I think reflects the interest of the field. We recently launched a design study website. So as you can see, we got all the links here, and there's a Google form linked at the bottom so that if you want to join our study, start attending our meetings, just fill out that form and you'll get added to the mailing lists. Lastly, we had a nice discussion with Elizabeth Gibney from Nature News about what this effort's about and what we're trying to deliver. Okay, so I mentioned on the first slide that we're working with other groups. We're working with other groups that are also interested in Wakefield colliders, but maybe coming from slightly different perspectives. And of course, we have limited resources, so we understand the value of working together and sort of forming our own Voltron of a collider collaboration to deliver as much as we can given resource limitations. So we really benefit by working together. We attend each other's meetings. We discuss, similar challenges. And I will give some explicit examples of how this collaboration sort of adds value beyond what any one of our individual efforts could do. But for those who aren't familiar, I think we already heard about linear collider vision, but basically the pitch is that one knock against linear colliders is that it's a big investment for a Higgs factory with no route to 10 TeV. We, of course, are arguing that there is a route to 10 TeV, and the infrastructure investment in a LC Higgs factory is also an infrastructure investment in a 10 TeV parton center of mass collider. I'll talk a bit about HAF in this presentation. This is an idea for a Higgs factory where plasmas are used to accelerate electrons, but conventional RF cavities are used to accelerate positrons. So it's an asymmetric collider. Alive is a proton-driven plasma collider. This is building off the AWAKE effort at CERN. and Allegro, which is this ICFA-initiated effort that organizes workshops and discussions. And yeah, so in the US, we focus on three high gradient technologies. So these are technologies that are aiming to produce accelerating fields on the order of gigavolt per meter, maybe larger. So those are structure Wakefield accelerators, where Argonne is sort of leading that effort at AWA facility, beam-driven plasma at SLAC at the Facet 2 facility, and laser-driven plasma at Berkeley at the Bella Lab. And all of these initiatives are supported by US universities as well as other national labs, universities abroad. So, for example, for structure Wakefield acceleration, Northern Illinois University, UCLA, very involved for beam-driven plasma. CU Boulder and UCLA are great partners. For laser Wakefield, we've got Maryland and Michigan and Texas and many others. So we really have strong university lab connections on these topics. And it's very good that we have a variety of options because each of these has advantages and challenges, and that plays into our thinking about future colliders based on these technologies. So what are the advantages and challenges of these technologies? I'm not going to go through all of this whole table, but I want to call out a couple different things. So structure Wakefield acceleration has a very nice feature, which is that it's acceleration in vacuum, which means that you can accelerate electrons and positrons equally well, same as for an RF accelerator. It's limited because it's a physical structure, so there's a maximum field, so we call that a breakdown limit. Plasma wake field, beam driven. So an electron beam comes in to create the wake, and then another beam subsequently rides the wake. That produces very high gradients, high efficiency. Our driver technology, which is just conventional RFLNX, is very mature. We do have a challenge with positron acceleration, and we have a challenge of staging, which is basically coupling multiple plasma accelerators together. For laser wake field, extremely high gradients are possible. So, 100 gigavolt per meter. There are compact staging optics because of the way you couple in light to various plasma sections. And they have a huge advantage of having near-term applications, which I'll discuss at the end. They also have the challenge of accelerating positrons in plasma. They have to further develop their laser driver technology. And all of these techniques have a stability challenge, which I will also address later in this talk. Okay, so there's a connection between the technology and the physics that these machines could potentially provide. So specifically, there's this challenge of accelerating positrons in plasma. I'm not going to go into detail and explain it. We wrote a review article that was published in 2024, so I'm now just noticing this typo that says 2014. It actually just came out last year, which goes into some detail about why it's hard to accelerate positrons in plasma. We do have techniques for accelerating positrons in plasma, but we do take a hit in efficiency, which means our luminosity per power goes down. So we're very interested in continuing this research and finding new ways to accelerate positrons in plasma more efficiently. But we're also motivated to consider, what if we don't have a positron acceleration arm? What if we just accelerate electrons in our machine? We could then collide electrons and electrons, or we could convert our electrons to photons just before the collision point to create a gamma-gamma collider. And then we have to ask, what's the physics for each of this machine? Electron positron, that's our benchmark. What about a gamma gamma or electron electron? So our design study goals are to consider the technology and the physics together, self-consistent assessment. We're not yet at the stage that we can point to a single technology and say, this is what's going to be the basis of our collider, but we are working in that direction. We need to understand the trade-offs, and we need to understand the metrics that we're going to use to evaluate the options. And critically, we're very interested in high energy reach, high luminosity options, but we're also interested in low cost options. So we need to understand how these things scale cost-wise as we try and reach the energy frontier. Our collaboration is divided into working groups. These working groups all have conveners who are listed in the backup slides. So the goal is for all of these groups to be talking to each other, understanding how the parts fit together, and making sure that one working group isn't expecting some unrealistic parameter at one part of the machine that another part of the machine can't provide. So everything gets propagated out to the source for self-consistent evaluation. So I don't get to talk about all the work that the different working groups are involved in, but I will highlight some specific examples and progress. So some recent developments. So first, I mentioned that we have to evaluate the physics case for electron-positron collisions versus electron-electron collisions versus gamma-gamma collisions. And Simon Knappen, who's one of our physics group co-conveners, he's from Berkeley Lab. He gave a presentation on this earlier this week, first talking about the methodology that they're developing for answering these questions. So basically, you give me some sort of collider parameters, some sort of beam parameters. We can then calculate a luminosity spectrum and calculate a physics output. And so based on that and some luminosity spectra provided by beam modeling team using WarpX, we're able to estimate how many particles or how many events of a certain type we can produce for a given BSM model. And one thing to highlight here when comparing electron-positron collisions and electron-electron collisions, so the top row is electron-positron, bottom row electron-electron, is that these are regimes of large Beamstrahlung. So large amounts of Beamstrahlung photons are generated, and those photons have a significant energy, and therefore they can be sources of new physics events. Okay, so this slide on the left from Simon's talk on Monday sort of illustrates how this process is done. So you consider a cross-section for some new particle, in this case, something with electroweak coupling, created either by two high-energy photons colliding or an electron-positron pair colliding, and effectively convolve that with your luminosity distribution, which is shown in the top right, to get the number of events per GeV for some assumed particle mass, in this case 3 TeV. And you're getting event generation both from electron-positron collisions and from gamma-gamma collisions. And on this plot on the right, what Simon finds is that you take a really heavy penalty for colliding just electrons and electrons and relying on the Beamstrahlung luminosity to produce new particles. So in the table on the bottom right, it basically shows the amount of luminosity needed for 5 sigma discovery, and you need far less integrated luminosity with electron-positron collisions than electron-electron collisions. So that's what's shown in this bottom table. So what does that tell us? It means that even if we take a hit on the efficiency of our positron acceleration process, even if that's a factor of 10, it still beats an electron-electron process. What's missing right now is repeating this study for a gamma-gamma collider where the electrons are converted to gammas by Compton scattering just ahead of the collision. That work is ongoing. Okay, I mentioned this Beamstrahlung question. These 10 TeV beams are extreme in all sorts of different ways. There's this parameter called upsilon, the Beamstrahlung parameter, where this one sort of is the transition between a classical and quantum regime. We're well into the quantum regime for most of the cases that we're interested in. The number of photons radiated per collision is much greater than 1, which means you get these very broad luminosity spectra. We have these powerful computing codes, which we'll talk about for a second, but we also want to have just some sort of analytical understanding for what's going on here. So I'm highlighting one result from our group that is in preparation. And here we are showing that in this sort of extreme regime, we find that there's a sort of universal function for the luminosity spectrum. So it always kind of follows the same shape. And this is basically because as you increase the beam energy, but keep other parameters fixed, the number of photons radiated in the collision stays constant, and that's what determines the shape of this spectrum. So this is an important tool that we can have, and it can really speed up our sort of our modeling and studies, because we can do an analytic calculation before having to turn the crank on some heavy simulation tools. I also want to highlight this result because it's led by an undergraduate student named Jaden He from the University of Maryland. He came to us via the DOE SULI program. He's a student. When you meet him, really gives you hope about the future of physics. Like there really are bright people entering our field at a young age, and I very much hope that we, as a community, can provide exciting projects for these students to continue to work on because it's a fantastic way. Well, it's fantastic to have his enthusiasm and his effort. It's also a fantastic way for us to get work done in a resource limited way because DOE pays for the SULI students. Okay, so I mentioned all these simulations. We have three teams working on beam simulations. So these are based on particle and cell codes. Um, each of these three teams comes from a background of plasma modeling and plasma acceleration. And in particular, the WarpX team at Berkeley, they won a major supercomputing prize for being able to model, really complicated plasma interactions. So now you have this fantastic code, this fast code, and you need to put it to work on problems of challenging problems that are important. And a great problem is beam-beam interactions. This is effectively a plasma interaction because you're talking about the interaction of charged particle beams, but it's complicated by QED effects. So there's been a tremendous amount of effort and a tremendous amount of progress going into this area. And each of the groups have slightly different points of emphasis. The WarpX team is really trying to reproduce all of the QED features in guinea pig. The Osiris team is trying to break guinea pig. By the way, guinea pig is sort of the community standard code for beam-beam interactions. It was developed by Daniel Schulte, who's now the head of the IMCC collaboration. Um, but it's like a single single CPU type code. It's quite old. There's a lot to be gained by pushing to these new high performance codes. There's a recent publication from the Osiris group in Portugal highlighting some ways where you can get real physics to deviate from what you can see in guinea pig. So you can model things that guinea pig can't model. Okay, now I mentioned at the start, emphasized the importance of collaborating with these other design efforts. So now I'm going to talk a little bit about the HAF collaboration. So what HAF is trying to do is design a machine, a Higgs factory, where the electrons are accelerated in plasma and the positrons are accelerated by RF cavities. And this avoids this problem of positron acceleration in plasma. It results in boosted collisions, which the field, we have boosted collisions at Super Keck B. We had them at Hera, so it's not anything super new. Um, but the overall size of this facility is 5 kilometers, so it's fairly compact for a Higgs factory. And when you have a concrete model for a facility like this, it really allows you to make a lot of headway in the detailed design of this machine. And so one of the things that HAF has been doing is looking at the interstage design. How do you couple plasmas together to produce a high energy beam? And so this little call out here is an example of how this would be done, including dipole magnets for coupling in and out the drive beams and plasma lenses for focusing the beams and sextipoles for chromaticity correction. And the wonderful thing about this is that this is very similar to the problem that we face for beam-driven plasma in the 10 TeV collider design. So we're working very closely with them to see how their lattice can be adapted for a 10 TeV wake field collider. In the low energy stages, it can be adapted exactly. In the high energy stages, we need to make some modifications. The HAF team is also looking very closely at this question of stability in the plasma wake field. So there was a paper about a decade ago from Lebedev, Borov, and Negaitsev at Fermilab asserting that there are challenges in being both efficient and stable in the plasma bubble when you're accelerating your beam. And their assertion is basically there's some limitation. You won't be able to extract enough energy from the plasma to be efficient without basically kicking out driving instabilities that will kick away your beam. You'll degrade the emittance. You'll lose charge. And since then, there have been multiple studies on how to avoid these instabilities. Ion motion is a particularly important way. And so this recent study, which was published earlier this month, explains how natural processes like ion motion suppress the growth of these instabilities. So this is extremely important for the viability of this technology, is that we have ways to damp out otherwise problematic issues that would grow over time in the plasma. Okay, continuing with the collaboration with HAF, they've developed an extremely important tool, which they're calling ABLE, the Adaptable Beginning to End Linac Code. And it's a multi-purpose code. It's both a simulation tool, but it's also an optimization and costing tool. So it is able to run simulations of the components of the machine at full fidelity particle and cell simulations, or using reduced models. So just say matrix elements to describe transport in the machine. And then it's able to basically run these mini experiments where it'll jitter some parameter and look at the output. So this experiment could be to study the stability of the machine, or it could be to study the cost of the machine. So by varying some parameter in the design, how does the cost vary? And you can see that on this plot on the right, how the cost of the machine changes with the number of PWFA stages, with the gradient, with the asymmetry of the collision, and all these factors are trying to be simultaneously optimized to minimize the cost of the machine. And this tool is not yet public. I think it will be deployed in September, but it's potentially a tool that could be applied to any accelerator design. So, it'd be really cool to apply this to the muon collider and just ask, what are the ways that we can minimize the cost of the muon collider? What knobs do we have there? Or any other future machine, future linear collider facility, or even FCC. Okay, so this is a very powerful tool. And once you have a powerful tool, you can just, ask the tool questions. So you can just ask it, design me a 10 TeV gamma gamma collider. And so Carl Lindstrom, who's my colleague at University of Oslo, and who wrote this, he just presses a button, says 10 TeV, spits something out. Uh, it's a bigger machine than I would have hoped for, 46 kilometers, and a cost of um, 14 to 16 billion in construction Swiss francs. We think that there are ways in which this type of naive design is imperfect. Specifically, we clearly have to address questions about the beam delivery system and not assume some sort of fixed scaling. We have to address questions about stability and spacing of these plasma stages at high energy, where we probably will not follow low energy design. So on the one hand, we take this with a grain of salt. On the other hand, as we go deeper into our study and deeper into designs, it's wonderful to have this tool that you can just basically change a parameter and then find out, did we get closer to our design goal? Maybe our design goal is just reducing the cost, and this helps us figure that out very quickly. Okay, so now I'm going to take a few minutes to talk about the outlook. So this design study is very important. It helps to focus us on what are the challenges that we need to solve on the path to this collider. But really the thing that's driving the field forward is our experimental R&D. So I'm just going to show you some examples about how this has progressed over the last 20 years. So in 2006, there was this first major energy doubling result at SLAC at the FFTB facility, where a 42 GeV electron beam was sent into a plasma, and then some of the beam electrons were accelerated to 84 GeV. So in roughly a meter. So this is energy doubling, 42 GeV energy gain in about a meter. And this is the beam spectrum. And you see it's kind of a continuous spectrum of particles all the way up to this 84 GeV energy. So there are experiments that kind of would benefit from dispersed single electrons at high energy, but certainly not colliders. For colliders, we need to have a beam at high energy. So this was followed on by experiments at SLAC at the Facet facility in 2014, where now we have two distinct bunches, one bunch creating the wake and then one bunch of electrons riding the wake. That second bunch gains 2 GeV energy, and now instead of having 100% energy spread, it has 2% energy spread. Daisy Flash Forward is another beam test facility offering even more precise control of the beam properties. And in that case, they got 40 MeV energy gain with an energy spread of 0.13%, and that is collider compatible. Separately, they demonstrated emittance preservation at this experiment. So really moving toward collider quality beams. But there's a trend here that you see, which is that there's an energy gain of 42 GeV, then an energy gain of 2 GeV, then an energy gain of 40 MeV. So you could maybe assume that we're sort of doing better just because we haven't given the plasma enough time to mess up the beam, right? If we continue this acceleration process longer, we'd get worse results. And so now, for the first time, we show that that's not the case. This is from Facet 2 data at SLAC this past spring, and this was our first high-quality multi-GeV experiment. So we got 6 GeV energy gain with 0.69% energy spread. So the energy spread is still a little too high, but it's showing that we can have very large energy gain, we can be efficient, and produce collider quality beams. This is, a great bit of progress for our group, but we're not done. We're going to continue to push, get higher charge, lower energy spread, higher energy beams, measure emittance, make sure that we're not destroying the beam in the process, measure charge capture. But this is a great first step for our program. And all of this has been enabled by improvements in our beam test facilities, which is really driven by support from the GUARD program. Okay, another big result. This was published 2 days ago, and there's this nice article in Physics Today about this result, where in a laser-driven plasma, they accelerate an electron beam, which they then send through an undulator, and it lasers. So they're measuring self-amplified spontaneous emission, lasing of their electron beam. And this isn't the first demonstration of LWFA FEL. This might be like the fourth, maybe, but it's the first where you're getting consistent lasing on almost every shot. And this is extremely important for our field. What we want is to get real world applications so that we have industry partners and that we do the exploratory R&D, we do the proof of principle, and that our industry partners do the detailed engineering that's going to be required to bring the costs of these machines down and hopefully get widespread adoption, beyond HEP. Because if we can rely on industry partners to reduce the cost of these things, then that's going to open up just a lot of possibilities for where we can take this technology in the future. The team at Berkeley is partnering with startups. So there was one startup involved in this project. There's going to be another startup involved in the continuing work there. And I think it's a great example of how our field can sort of continue to build the sort of societal infrastructure that will be needed to one day support a Wakefield collider. Okay, so lastly, I mentioned that we've developed these particle and cell codes, which are extremely powerful. And once you have a hammer, you go looking for nails. And so these beam codes, they're not just for Wakefield colliders. They can be applied to any future collider. And so what you're looking at are some pretty movies that my colleague Ariana Fermenti from Berkeley Lab has made in WarpX for FCC and ILC. These codes are going to be faster and more robust than Guinea Pig, which is the community standard. They're going to be better documented. We're working with HEP experimentalists to include the beam into the software stack. So you run the beam, you generate your backgrounds, you propagate them to the detector. So we're doing all of this inclusively. We're very much engaged in the HFCC effort and excited to be contributing to design and improvements of future Higgs factories. And of course, just from the standpoint of communication, having pretty pictures is important. So at minimum, this tool will be useful for that. Okay, that's it. I'm very excited about the work that our collaboration has been able to do in less than a year. As Tova mentioned, we're sort of scrappy, not really funded from any particular place. We're making the most of our resources. We would love more resources, of course, but we also, want to make the best use of what's available. And we're driven by people who are excited about this, who are able to, put some of their time into it. And if you want to learn more, we'll have presentations at the upcoming North American Particle Accelerator Conference at Sacramento in August, as well as Lepton Photon in Wisconsin, EAC in Italy, and LCWS in Valencia, Spain. The Allegro workshop next year in Frascati. And if you want to learn more, you can go to our website and use the Google form to join the study. Thank you.
Okay. Thanks very much, Spencer. You got a question from Heidi, who asks, what timescales could one estimate, given ILC and LHC experience, for R&D need to do a full technical design?
Great question. I think that there's two ways to break that down. So one is the immediate R&D demos that are needed are staging of plasma accelerators and this possible resolution of the question of positron acceleration in plasma. So what I can say is that we don't yet have an answer for the positron side. So we're leaning toward electron acceleration only with conversion to Compton conversion to gammas with a Compton interaction for a gamma-gamma collider. So that would require a staging demonstration, which is something that could be achieved, on the order of 5 years at the appropriate facility. We would have to modify existing facilities at some cost. So, if we had ample funds to build a staging facility now, we could have a result on that in 5 years and then move on to technical design. Knowing what I know about the long-term development of these, it would be great if something like that could happen within the decade. But this is more of a decadal plus effort to work toward a technical design.
Are there any more questions? I'm not seeing anything in the online or in the chat.
Yeah, I think people know how to get a hold of Spencer if they do have more questions. So